What we'll do in the video today is use calculus to help us find stationary points for functions. So you might remember at the start of the year we were sketching cubics, and what we'd try and do is factorise the cubic, so we'd get it into factored form, whatever it might have looked like. Then use the null factor law, so let that equal 0, solve it, and what we would get is the x-intercepts. And often the question said not to worry about providing the exact coordinates of the stationary points, so these things here. And that's because we didn't have a method to actually do that, but now we can do it. So just a little bit of preamble on stationary points. So the graph to the right here, this one here, we've got 3 possible stationary points. So there is a stationary point at point A, that's this one here. So that's what we call a maximum stationary point. Okay, it's not the maximum value of the function, but it's what we call local max. All right, now the highest value of the function usually is this one here. If it continues indefinitely, we'll continue off in that direction there, we only presume. So that would be the absolute maximum. This is the local maximum. This one here, because we know it says that there's stationary points at A, B, and C, this one is here is what we call a stationary point of inflection, or a SPOI. Now just note that functions can have this kind of behavior, and it actually will not be or may not be a stationary point of inflection. So it could be a point of inflection, or it could be a stationary point of inflection. We know that this one is because it says the graph to the right has stationary points at A, B, and C. So this one here is another stationary point. We call this one the local min. Okay, so let's use some calculus now to help us find the stationary points of the following functions. So this is a parabola, and we can find the turning point or stationary point on a parabola by using something like x equals negative b onto a and putting that into the original function. But let's just use some calculus on it. So the way we'll do that is get our derivative function. Whoops, bad start. And then what we'll do is we want to know when dy dx, or the gradient, is equal to 0. So we set dy dx to 0. And what we're going to do is solve for x, and that will tell us the x value where the gradient is 0. So we'll go negative 12 equals negative 4x, x equals 3. Now don't forget that what we'll need to do for that is that only gives us the x value. We need to actually put that back into the original function to find out the value of y where the stationary point occurs. So we're going to sub that into there. Right, so we'll go y equals 9 plus 3 times 12 is 36. Take away 3 squared is 9, 18. Take away 18. So that's going to be 36 take away 9 is 25. So the coordinates of the stationary point are 3, 25. Now again, you can do that with x equals negative b on 2a because that works on parabolas, but it doesn't work on cubics because we've got no real mechanism for finding out the stationary points of cubics. So this time around we have to use calculus. Now note that we're going to get the stationary points of this where t is greater than 0. So let's get our derivative, dp dt equals 6t squared, take away 10t, take away 4. All right, so our derivative function is this. Now we're going to ask the derivative when it has a gradient of 0. Let's make an easier function to factorise by dividing both sides by 2. T, 3t and t, and what have we got? 2, 1, and negative 6. 0 equals 3t plus 1, t take 2, t is equal to negative 1/3, t is equal to 2, but t greater than 0, therefore t is equal to 2. Alright, so now what we'll do is sub that into this original function here. P equals, that's 2 cubed is 8, that's 16, take away 5 4s are 20, 4 2s are 8, -4, -12, plus 13 is 1. So the stationary point where t is greater than 0 is 2, 1. It does have another one, but we're going to reject it because it's out of the domain. This function is only true for t greater than 0. All right, this next one, we've got this function here and we need to find the stationary point, so let's get our derivative. Set the derivative to 0. X squared equals 1, x equals plus or minus 1. All right, so we'll sub that in. So we've got y equals, so let's go positive 1, which is 4, plus 3, take away 1, which is 6. So 1 comma 6 is one of the stationary points. Let's put negative 1 in, y equals 4, take away 3, negative 1 gets cubed and is negative 1, plus it, plus 1. It's 2. So the other one is at negative 1 comma 2. So it's got two stationary points, one here and one here. Alrighty, this one here, we've got this function and we want to find the stationary points. So we'll go dy dx equals 3x squared plus 1. Set the derivative to 0. X squared equals negative 1/3. X equals plus or minus, and we'll note that we're about to square root a negative number. So we're going to say, instead of saying x equals, we're going to say x squared equals negative 1/3 is not real, therefore no stationary points. Okay, and it's interesting to note that not all cubics have stationary points. So this is the graph of x cubed plus x. Looks like it's got a stationary point of inflection at x equals 0, but calculus begs to differ and it says it's never got a 0 gradient. Okay, so this one here is what we call a point of inflection. It's not a stationary point of inflection. And in fact, we can find out the gradient at that point by simply subbing in 0 into the gradient function and noting that the gradient at that point is 1. So the equation of the tangent is y equals x as it runs through there. Okay, so it doesn't have a gradient of 0, it has a smallest gradient of 1. All right, the final question is your classic simultaneous problem. The curve with the equation blah 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 passes through 0, 5. So let's write it out with its y-intercept. Therefore, c equals 5. Make sure you write that down because we need to find a, b, and c. So I've found c. Then what we'll do is we'll sub 2, 7 into the function because I know it goes through 2, 7. Let's clean that up a little. Alrighty, now we need to develop the second equation. Now I've used this point already, and I've used this point. We need a third point. And it comes out in the wording that, in fact, this point, along with the original function going through it, also has a gradient of 0 because it's a stationary point. So that means if I get dy dx, which equals 3x squared plus 2ax plus b, what I know is that when x is equal to 2, at this point here, the gradient is equal to 0, that thing there. So let's pop 0 in. 3 4s are 12 plus 4a plus b. Negative 12 equals 4a plus b. Okay, so let's call this 1 and call this 2, and we'll do 1 take away 2. So that's negative 6 take away negative 12, 6. 4a chops out, 2b plus is equal to b. So b is equal to 6. Then we'll just sub that into one of the equations, doesn't really matter which one. Negative 12 equals 4a plus 6. Negative 18 equals 4a. A equals negative 9 on 2. Alrighty, so 18C is your starting point, and then several worksheet questions to really finesse your understanding. This is a fundamental skill for year 12. You'll do this heaps and heaps and heaps of times. Now I'm just going to show you quickly how to do this on the calculator as well. So let's just take this function here and I'll show you how to run the same thing on the calculator very, very quickly. So the first thing we'll do is define our function. So shift 7 will give us f of x equals, let's type it in, 2x cubed, take away 5x squared, take away 4x plus 13. All right, so what we're going to do is get our derivative functions. So we'll go shift and minus to get diff, and then we'll go shift and 8 to say, can you derive f of x, please? Gives us that as the derivative function. All right, now the next step is we want to solve or set that to 0 and solve for x. And we can do this in one line. So we're going to go shift equals for a solve. And we're going to go shift execute to get ants. That's this thing here, equals 0 for x. That is, tell me what value of x makes the gradient function 0. And it goes 2 values. Now this one here, remember we discounted that, and so this is one of the values here, x equals 2. So then we're simply going to go shift 8 to get f of x, change that to 2, and it's at 1. Okay, so this one would really be a fairly easy 2 to 3 mark question in exam. What you would do is if you've got that function there, you would go f dash x equals 0, x equals 2, x equals negative 1/3, but x greater than 0, therefore x is equal to 2. And then you would say something like f of 2 equals 1, therefore coordinates are, when x is equal to 2, the y value is 1. Okay, so we really don't need to actually do a lot of actual calculus on exam 2 type questions or calculator questions. We simply show our working out and let the calculator take care of the hard work for us. Good luck with that.